Hey everybody, it's Mr. Gear. I'd like to introduce you to somebody. His name is Travis Berkley. He's a steely-eyed missile man. I've known this man as long as anyone who's not a member of my family. And he's amazing because he made for me this clock. No, really, it's a clock. Let me see if I can explain to you what's in it and how it works.
Now, the concept of telling time using a mechanical device is centuries old. Digital clocks, though a relatively recent invention, simplify the process greatly, but they do have to translate from the original binary language of computers to the base 10 system we're accustomed to. I have owned this clock from ThinkGeek for several years, but it has three basic problems. One, it's starting to fail on me. Two, it's really too small to use in a classroom environment. And three, it reads in a sort of pigeon binary. Although it does read in binary, it uses tens and ones, tens and ones, and tens and ones in hours, minutes, and seconds, which is not really binary. It's a nod towards the base 10 system that we're accustomed to, and I'll give you three guesses why we use a base 10 system. So I told Travis that I was interested in coming up with a clock that would read in real binary and be real in size. And he and I chatted back and forth about how we'd go about doing it. And because I am horrible at such things, I just kind of left it at that and never thought about it again. Travis, because he's a better man than I am, went to work. He bought an Arduino trinket and programmed it. He bought an RTC real-time controller chip to go on it to actually have it keep time. The Arduino is for the purpose of making the lights light up and use that time to display. And built this whole thing from scratch, including the case. So how do you read it? Well, it turns out that from top to bottom it reads exactly like a clock. Hours, minutes, and seconds. But reading what each row means takes a little bit more explanation. In the standard base 10 counting system, we count. We create a column, we'll call it our ones, and in it we put our value. When we start with 0, and then when we count up one more, we change from a 0 to a 1. And when we count up one more, we change from a 1 to a 2. And we keep changing our digits until we get up to our maximum possible digit, which for us is a 9. This column is now full, and the solution I need to do now is create another column. We'll call it the tens column. We're going to have to reset our ones column, and we'll count now 1 in the tens column. Now we'll keep counting up and we'll keep adding values, and when we fill up our tens column, it has 9 in it now, we're going to need another column. We'll call it the hundreds column. We'll reset what's in the tens column. It goes back to 0, and now we have 1 in the hundreds column. We create numbers by continuing to count and adding in each of those columns. Let's say we have 2 more tens and we have 5 more ones. That gives us a total of 1 in the hundreds column, 2 in the tens column, and 5 in the ones column. And when we add all of those things up, we create 125. In the binary counting system, or base 2, we do it exactly the same. If we have some numbers to count, we create a column and we call it our ones column. We start with nothing and we add up 1 and create 1. But this column is now full. So what we need to do is create another column. Only it's not going to be worth 10. We're only counting by 2, so it's going to be worth twice as much, 2. We'll reset what's in the ones column, add 1 to it and make it 0, and then we'll add 1 in the twos column. Count up again, we'll put 1 more in the ones column, and now everything's full. If I need to count 1 more, I need another column. Double the twos is going to be 4. Now we'll put 1 in the fours column, and the other 2 will reset to 0. Count up again 1 more from there. We put 1 in the ones column, and what we have here is a full number with 1 in the fours column and 1 in the ones column for a total of 5. Now, to be clear, this clock reads from left to right. So the leftmost column in each of these rows is 1. The next column is 2. The following column is 4. The next is 8. The next is 16. And finally, the rightmost column is worth 32. And if you have a 1 in each of these columns, you can count to a maximum of 63. All right, let's stop time here and see if we can make sense of it. On the hours row across the top, we have nothing in the ones or the twos column, but we do have lights in the 4 and in the 8 column. 4 and 8 together make a total of 12, so it is 12 o'clock. Going down to the minutes column, nothing in the 1 and 2, but something in the 4 and the 8, not the 16, but the 32. We have to add those together. 32 and 8 make a total of 40, and add another 4, and you wind up with 44. It's 12:44. How many seconds? 1 lit, 2 not. 4, 8, and 16 lit. Let's add those up. 16 plus 8 makes 24. Another 4 makes 28. Add 1 more, you have 29. The current time is 12:44 and 29 seconds. Now let's let it run and we'll count up with it. 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, and we add one more to the minutes column. So there you have it. My students are going to have an awesome time learning how to read this, mostly because I got rid of all the other clocks and they have no choice. If you ever need some awesomeness, here's the man to call. Love you like a brother, Travis. Thanks.